Okay, so I guess I'll start with thanks too in kind of both directions. So I don't know, is Chris here? So I guess the first should be to my advisor when I was a PhD student here, Chris Manning, who really got me started on all of this. But in the same time, in the time since I've been at Berkeley and had a bunch of amazing collaborators who have really formed the backbone of everything else I'm going to talk very briefly about today. So I feel like I've been supported on both sides, and it's been an amazing experience. And so thank you to everyone. So I'm going to talk today about is the general shape of the work I try to do, and this is the work that I started here at Stanford. And in general, there's a lot going on in language. So in particular, there's syntax, and these are, the examples here are small. You're not meant to read them. But there's the structure. If you diagram sentences, that's one kind of structure in language. But there's a lot more. There's discourse structure, what various things that we say refers to. This is the reference resolution that Sebastian was talking about. And then there's semantic structure as well. And this is not only linguistic. So if I point it and I say they're on the front of the table, it's some combination of the words I'm saying, the visual perceptive environment I'm speaking in, and maybe some gesture as well. And all of this needs to somehow be integrated, and it's all quite complex. The thing that's hard about it is that the standard machine learning techniques where you specify what each piece does, those don't seem to work because we don't really know what's going on. We just know, this is the data and this is how it seems to be used in practice. So my inspiration was the only method that, the only system that I know of that does actually acquire language, and it looks a lot like this. And we don't really know how this system works, but we can be inspired by it anyway, which is essentially all of this data comes in. And there's some large amount, some combination of the data and the processing, and from this emerges an understanding of a grammar that is not explicitly declared. Okay? So I want to build systems that work roughly like this. And this basic idea that most of what's going on in the data, you need to learn from the data itself using statistical methods, has actually let us get pretty far with some of the kinds of natural language processing that have been standing challenges. So the work that I did here mainly concentrated on syntactic analysis, where the question was, from all of these surface strings, can you figure out the grammar that underlies them? And the answer that I was hoping the answer would be sometimes, and it turned out that it's quite possible if you have the right models. And that was a surprise to me, and I think to a lot of people. Since I've been at Berkeley, we've tried to extend this kind of approach where now we can take what we do have in language and learn kind of very fine and detailed models of what's going on. So what one of these diagrams shows is you may have learned that there are words like the or a, which are determiners. Well, okay, that's a very simple description. What's really going on is much more complex. There are quantifiers, there are demonstratives, and these things are kind of all subtly different. These systems now automatically figure all of this out from data, and as a result, you can use these methods to build the most accurate parsers that we currently know how to build in the world. And at the same time, and just to give an example of another task, in entity reference, this is also how you can build the most accurate systems for entity reference, all unsupervised. These actually work better than the kinds of fully supervised methods that people had tried before. Okay, so why do you want to parse sentences? Well, one thing you can do with it, and Sebastian raised this as well, is you can do things like machine translation. You might wonder how systems like, if you've used the Google machine translation system, how they work. They basically work by remixing translations they've seen. So part of this equation is getting millions and millions of example translations and recycling them well. Okay, but what does it mean to recycle them well? Well, what it means is you've got some database. So in this case, there's only 2 example translations in my database, but there'd really be millions, and that's its own challenge. And the way a machine translation system will work, and we work on these kinds of things as well at Berkeley, is that I see some new example, like what's shown on the bottom. And what I want to be able to do is say, well, in my training set, I've seen examples, and I actually understand the structure of those examples. So what I can do is I can see, all right, well, there's this word después, which I have seen somewhere. In particular, I've seen it in the right example, and I know kind of how it translated. How do I know that alignment, that linkage, that después here means this adverb later in English? Well, that's an unsupervised alignment problem. We work on that, and we've got currently the best system for doing that kind of thing. But basically, you continue this. You find each of the pieces you need to build up in your training set, and that lets you construct this translation. And the core of all of this, once you've got these examples, is understanding how they decompose and how they connect up. And that alignment problem is the unsupervised learning problem we work on in translation. Okay, so just to give you a sense of what these things do if you don't use them, this is an output from a web-based translation system. This is actually Google's. And, well, if you read French, this is great, but if not, that's just a bunch of words. But if you then feed this in, out pops the exact same thing in English, and it's actually pretty good. It is impossible for journalists to enter Tibetan areas. Philip Bruno, correspondent for World in China, said that journalists of the AFP who have been deported, and so on. So these things actually work quite well. And the things that you need to make them work is lots of data, and the world's kind of providing that, and these kinds of unsupervised methods to link it all together. Okay, I'm going to give you one more example of the kinds of things that you can do when you've got a lot of data and really good unsupervised learning methods that we weren't able to do before, and that I think are going to be important going forward, is we can answer a lot of questions about language and where it comes from and where it's going that we weren't able to do by hand, even with lots and lots of knowledge of how language works. So an example of this would be if I take I can collect data where, for example, I can these are some languages in the Oceanic group, which probably the one you're most likely to know is Hawaiian. There's a bunch of words in each of these languages that mean break, and those are shown here, and a bunch of words that mean house. These are what are called cognate groups. They're all kind of words that mean the same thing in related languages, and if you look at them, you can see they're kind of similar. Right? They're not all the same word, but it's not an accident. And the reason it's not an accident they're similar is because they descend from a common language. And people have spent a lot of time by hand both trying to figure out what that tree of languages is like and also trying to figure out what the early ancestral forms are. And what we can do now is we can use these same kinds of unsupervised learning methods to take not just one or two words in one or two languages, but to take hundreds and hundreds of languages and hundreds of words and build these gigantic trees that are basically automatically reconstructed phylogenies of how the languages have descended. And that's something that, that these systems can do quite well. But the particular work that we're focusing on is not just assembling these trees, but actually trying to reconstruct the ancestral forms. So in this case, the way this proceeds is you learn from all of this data the kinds of connections between sounds. You learn how sounds change in general. For each one of the specific branches in this tree you've reconstructed, you learn what process was active there. It's kind of like biology where things are mutating, but instead of mutating at random, they mutate in a characteristic way that's characteristic of that link. And then what pops out of this at the top is actually reconstructions of the protoforms. And this lets us do a lot of things that we couldn't do before, like take thousands and thousands of languages and try to reconstruct back quite far into the language tree to see what the words of the ancestral forms might have been. It also lets us answer questions about how language works that you can answer when you've got thousands of languages, that when you tried to figure out the same statistics on 4 languages by hand, there just wasn't enough data to say one way or the other. So that's it.